Hi, everybody. Welcome to our presentation, AdaCore. So in this presentation, we will present a design and implementation of embedded oscilloscope. The team are the team from University of Ottawa are Anne-Sophie Cousson, Jean-Sébastien Demers, Basma Kanan, Florian Koujonou. So this is our table of contents. Number one, scope of the project, overview, the challenge. Number two, preliminary research, a similar project, our choice of technology. Number three, design, component, target design, host design. Number four, implementation, firmware, graphic interface. Number five, challenge and thought on ADA. If it's possible, we will have some demonstration and conclusion. So project of scope. The University of Ottawa's software engineering program is collaborating with AdaCore for a Capstone project. My name is Mohamed Ali Ibrahim. I am regular part-time professor at the University of Ottawa. And Olivier Henley supervising the team of 4 students. The team design and implement an oscilloscope based on STM32F4 microcontroller using Ada and Spark programming language. The challenge. So the challenge, main objective, design and implementation of real embedded software oscilloscope based on STM32 microcontroller using Ada and Spark programming. The student had no prior experience in Ada, in Ada. So the learning about advantage of Ada or embedded system and how to use the language. So the student also learning to implement Ada, ADC, DMA, and UART in Ada, implementing a communication protocol between target and host throughout UART. The student use, so we are using development Linux on Linux. So the project starts in January. The project is 8 months project. So we start January, and the first first semester we already have a first working prototype and documentation. So, and then the student will restart in September because the students are going to work a summer internship. So we will present what we done so far. So they will start in September, and the project will finish in December. So they will add new feature and refine solution, and the project will finish in December. They will have a presentation. So they will start. So the student can start now. I think I will stop sharing my screen now, and the student can start sharing.
Yep. Thank you, Olivier and Mr. Ibrahim. So I'll just share my screen.
So I have to stop my sharing screen.
Can you see my screen?
Yes. Yep.
Yeah.
Okay, perfect. So now we'll talk about the preliminary research that we've done. So in terms of similar projects, multiple embedded or PC oscilloscopes already exist. One example would be the Picoscope 2000, which is a small device that you can connect to your PC by USB. It supports multiple channels and has a sampling rate of 1 gigasamples per second, has a bandwidth of 10 to 100 megahertz, and supports an input range of up to -20 to 20 volts. We've also seen someone make an embedded oscilloscope on an STM32F4 board using the built-in display instead of connecting to a separate computer. On that board, they were able to have a 7.2 megasamples per second sampling rate and a native input range of 0 to 3.3 volts. So we'll be using these measurements to know what we can expect to achieve using the STM board. Let's talk about the technologies we've used for the project. So first off, we're working with an STM32 board. The specific board we're working with has a Cortex M4 processor and contains all the necessary hardware components that we need for the project. It also has an existing Ada runtime and working drivers, which is great because we don't have a ton of experience with embedded software, so that gives us a foundation to work from. Of course, we're also using Ada, which, as you know, is great for embedded systems, helps minimize runtime errors, and it's a great opportunity for us to learn a new language. For the user interface, among other packages and tools, we're using JTK Ada and the Ada Industrial Widget Library made by Dmitry Kazakov. We're using Linux, specifically Ubuntu or Mint, as a development environment, and also to run the user interface. We're using Alere, which is a great tool to help manage the dependencies for our project. And finally, we're using OpenOCD to load firmware onto the board.
All right, thanks. So now we'll take a look at the high-level design of our project. So let's start with the components overview. It's pretty basic. We have our target, so the STM32 board. Its role is to read the voltage coming from a tension source. It then sends that information to the host computer via a mini USB cable. And then the host reads the data and displays it in a graph. For those who like diagrams, here's a really simple system diagram showing what components we're using on the board. So of course, we have the CPU or MCU, the timer, some memory, the UART1 and the ADC1. And we will explain the specific role of each of these components later in the presentation. So let's take a look at the high-level code architecture. Again, this is fairly simple, but since it was a first embedded systems project, we wanted it to keep it simple and not to make it too complex. So on the host side, so the computer running on Linux, what it does is it reads the voltage value coming from the serial port and then stores that voltage in an array. We then keep doing that until the array is full, and we display the contents of that array in a graph. And then we repeat the whole process over and over again. On the target side, we have a tension value where we read the tension value from the ADC and then convert it to a character and then send it to the serial port and then repeat until we finish sending a whole number. And now let's let JS continue with the implementation.
Great, so now we'll talk about the implementation of the project. In terms of important modules for the target, we're using an analog to digital converter to convert the analog voltage into digital values. We're also using a UART to communicate with the user interface running on the host PC. The board has 4 UARTs, and UART1 can be used through the mini USB port, so that means we don't need to use a separate USB cable connecting to the pins on the board. And finally, we're setting up a GPIO pin to work with the ADC. We also use OpenOCD to load the binaries onto the board, and we use drivers from the Ada drivers library. So let's describe the code running on the board. We start off by initializing the ADC with DMA using a GPIO pin. Then we continuously read the voltage values coming in from the ADC. These values will be between 0 and 3000 millivolts because we're using a reference voltage of 3 volts. Then we send those values to the UI through the UART. We can send 8 bits at a time, so we're converting the voltage values to an array of characters and sending them in the form of their ASCII representation. The image on the right is just an image of the testing setup we're using at the moment. Our final plan is to test it out with a function generator, but for now we're using a potentiometer.
So we now switch over to the host. So we'll start by looking at how we can read data coming from the board. So we decided to write all that logic as a function, since it will make it easy to modify our parameters and it would enable us to use it wherever we want. So we have 2 parameters. The first one is the number of samples that we want to store in our array, and the port name. So the port name is to specify where we want to listen for the data. And then the function simply returns the array of stored numbers. For now, the way that we read the data is really simple, but we plan on improving it. We'll talk about it later in the presentation, but for now, here's how it works. So first, we actually, you can go back to the first slide, to the previous slide, no worries. So first, we open the port with the name specified as a parameter, and then we instantiate the 4 variables. So first, our buffer, which is a stream element array to read from the serial port. Then we create a line, which is a string to store every digit of the number received from the serial port. And then we have our line index to be able to build every index of the line. We also have a readings array, which will contain all of the numbers received from the serial port. And this is what also the function will return. So we then read the serial port. If we read a character that is not a line ending, then we store it in a line variable and then repeat the process so we can build up the next digit of the number. But if it's a line ending, then we convert the entire line variable, which is a string, to an integer, and then store that integer in the readings array. And then when the size of the readings array reaches the number of samples that we have specified as a parameter, we exit the loop and then return to the array. We return the array with all the readings. So now we can take a look at the UI. So on the UI side, we're running on Linux. We are using also GTK Ada for our graphics. On the oscilloscope side, we simply did not have the knowledge nor the time to build a great UI, but thankfully we were able to find the AIWCL, which stands for Ada Industrial Widget Control Library. And this library is made by Dmitry Kazakov and was really helpful. So it's more complex than the read function, but there's a simple explanation that we have. So first, we start by setting a bunch of different parameters for the graph. So like the number of channels, the scale, the increments, and all of the UI stuff. And then we display that graph. Then we start a new task that runs in parallel. And that task will call the read function that we talked about earlier with the desired parameters. And once it receives what the read function returns, then it feeds all of those points into the graph that then displays them in real time. And we repeat the whole process of calling the read function and then displaying the points in the graph. And since it all runs in a separate task, we can simultaneously display the graph and updates the points on the graph. So this is a little screenshot of the UI, but you'll have a better look at it later. So I'll let GS continue with the next section.
All right, so now we'll discuss the challenges we faced and our thoughts on Ada. We were initially using the board on the left for our project. The main problem we had with this board was that we would have had to work on some linker scripts and a few other things to make the Ada runtime work, and the existing drivers were also not configured to work as is with that board. And this would be fine if we had a lot more experience with embedded software, but we're still pretty new to the field. So after discussing these concerns with our client, we came to the conclusion that switching to another board that has existing working examples in Ada would be best to continue the project.
So we used Ada mainly because it was requested by our clients, but after diving into it, we discovered a lot of cool sides of this language. The language was designed for a secure and reliable real-time and embedded systems with many safety-critical support features, so making it perfect for our application. We had the chance to dive more into like Ada's future. This includes like strong typing, model programming mechanisms, runtime check-in, exception handling, and so on. So in terms of quality, Ada is really not about what it can allow, but rather what it doesn't allow. That makes it really stand out. We were very astonished by how it can really complain about the smallest issues. Next slide, please. So in another side, Ada was completely a new language for all of us. So we were faced with a steep learning curve at the start of the project. The learning process was challenging due to the limited amount of resources available for Ada, such as tutorials, examples, and code samples, and libraries, and so on. So compared to more popular programming languages, and since Ada is not as popular as it used to be, a lot of resources that were available were outdated or no longer working. So we had to brainstorm about what resources we can use. One example was the STM community, where people ask and answer questions about anything related to STM boards, for instance, and also like several GitHub repositories of existing Ada projects. Now I'll let my colleague continue with what's next.
Thank you. So yeah, what's next? What are you working on? So first in June, so this month, we want to polish our processes. So during the last semester, we spent a lot of time during just coding and trying to make everything work. But we did not really take the time to document everything. So now we want to take a step back and update all of our documentation. We want to update GitHub and Jira so we can go back to school in September and be well organized and be ready to go. And then on July and August, we want to take a look at the communication protocol. So as you saw it right now, it's pretty basic, but we want to make it more reliable. We want to be able to send data from multiple channels, and we also want to make it faster. And then for the next semester, we want to finish working on the new communication protocol. We also want to be able to analyze at least 2 channels simultaneously. Another cool feature that we would like to implement would be to have the ability to save or export the data from the oscilloscope to the host computer. So that would allow us to look at the results later on. That would be good. And finally, we would also like to be able to control certain parameters of the board from the host computer. So for example, changing the sampling rate or deactivating or activating one channel and stuff like that. And that's pretty much it for now. So I'll let JS for a quick demo now.
All right, great. So yeah, we'll show what we have so far. I'll just hop into my VM. So yeah, here you can't see it, but I have the STM board connected to my laptop. So as I mentioned previously, to test it out, we're currently using a potentiometer that's connected. There it is. Okay. We're currently using a potentiometer that's connected to the GPIO pin set up to work with the ADC. Eventually, as I said, we want to test it out with a function generator, but we have a potentiometer for now. So here I'll just run ALR run to run the UI. And there it is. So yeah, since it's a potentiometer, the values are fairly static. But if I adjust the potentiometer, we can see the values change. And yeah, so as Florian mentioned, eventually we want to be able to add multiple channels and adjust a few other parameters. Yeah, so I think that covers our presentation. Thank you very much for listening, and we'll be happy to answer any questions if there are any.